Hello, everyone. Thank you for joining us. I would like to introduce Dr. Thorsten Wuest to you. Dr. Wuest is an assistant professor and J. Wayne and Kathy Richards Faculty Fellow in Engineering at West Virginia University, and he's globally recognized as one of SME's 20 most influential professors in smart manufacturing. Dr. Wuest has co authored 3 books and more than 130 refereed journal and conference articles gathering almost 2,500 citations to date. He received several awards for his work, including Outstanding Teacher of the Year in 2019, SME Journal Award, and Best Review Paper Award by the International Journal of Automation Technology. Please welcome Dr. Wuest, who will be speaking on the topic of artificial intelligence in smart manufacturing systems.
Thank you so much, Teresa.
You're very welcome.
Welcome, everybody. Thanks for joining us today. As Teresa mentioned, I will talk about artificial intelligence and what relation that has to our smart manufacturing systems. Very relevant topic, very hot topic, and we try to make some sense of that today. My presentation is structured in 4 main parts. I will give a quick introduction just to give a scope and put the topic into a frame. Then talk about artificial intelligence. Where are we at that point? Why is it so hot right now? Then give you a few tangible examples of how AI is applied in smart manufacturing systems, and then try to give a bold outlook and some reflections on what we talked about. All right. Without further ado, I want to recognize my team at West Virginia University that contributed to this presentation, as well as the overall work and output that my lab provides. Also, of course, our sponsors from the Department of Energy, NIST, industry, and so on that make the research possible that allows us to develop this topic further. The research focus of my lab is, quite obviously in AI and machine learning in manufacturing, smart manufacturing and Industry 4.0, hybrid analytics, where we try to combine data-driven analytics and physics-based modeling, product lifecycle management, and product service systems. All right. I also want to take this opportunity to mention our new book that came out this summer. I believe it's a very timely work given the COVID pandemic and all the interruptions that we face in supply and value chains. So far, it has been very well received, and this presentation actually is based to a large portion on what we discuss in the book. So I encourage you to pick up a copy and send me your feedback. All right. So enough self-promotion. Let's jump into the topic. And before we do that, just as an intro. I mentioned the pandemic before, and this pandemic has caused quite some trouble with supply, with manufacturing, with our companies globally, but also in the U.S. And together with, for example, Andrew Kuziak, who will be a panelist or will give his speech tomorrow. We looked a little bit into how AI actually aligned with some of the impacts that we experienced from COVID. So, for example, travel restrictions, workforce stay-at-home orders, and social distancing. And we found quite some overlap between companies that apply AI-based technologies, such as predictive maintenance, augmented and virtual reality, with mitigating these impacts from the COVID-19 pandemic. During the first lockdown. So this is quite interesting, and also aligns with the strategic goal of a lot of companies. Hopefully, they will now take this massive short-term investment and try to align that with their long-term strategic goals and make sense of these systems and the data that they provide. All right. I will not go into detail on the 4 industrial revolutions so far. I'm pretty sure everybody listening in here has heard enough about that and is familiar with it. What I want to do is put the context of connectivity in here, because connectivity is basically the foundation for all Industry 4.0 technologies. We need to connect on and beyond the shop floor, our assets, our users, our items that provide data. That connectivity allows us to connect the virtual world with the physical world. And most of you probably heard of or working on digital twins and other frameworks that work on this connection between virtual world and physical world. This connection, like bringing the physical world and the virtual world, is fueled by data and making sense of data, using data for value-added actionable insights, right? And this enables us to be competitive in the manufacturing space and produce high-quality products at a reasonable price. I believe this development is not optional any longer. It's a necessity, especially for manufacturers in high-wage countries such as the US or Western Europe. But we see a large investment in these technologies from developing or emerging economies as well. So I believe there's no time anymore to say like, oh, we're not interested in that. That will not go well for long. All right. So now the introduction stated about Industry 4.0, but what does that really have to do with AI? Well, to answer that a little bit, I want to put our understanding of Industry 4.0 into context with, excuse me, two items that feed into that. On the one hand side, we have advanced manufacturing, which in our understanding focuses on the physical manufacturing technologies. So advancement in additive, advancement in laser cutting, advancement in injection molding with sensors built in the dies. These I would all put into the advanced manufacturing side of things. On the other side of the medallion, we have smart manufacturing, which focuses more on the data and the data analytics. Some of you might now argue that, hey, additive manufacturing is a inherently digital technology, right? You cannot do that without having a digital model. And you're right. These are not contradicting. These are two sides of the same medallion. So both have, of course, a large overlap and work hand in hand. Additive systems and modern CNC machines provide a lot of data that we can then use to do advanced analytics and feed that back into the control unit. So this is our understanding on what the two main pillars of Industry 4.0 are, advanced and smart manufacturing. And today we will focus more on the smart manufacturing side of things. Smart manufacturing, discussed broadly, a lot of different understandings there as well. But we broke it down into three principles or principal pillars. The first one, connectivity. We have to connect our physical assets, and manufacturing still is grounded in the physical world. To collect data, to access them, to communicate with them, right? And that leads to virtualization. We have to bring that physical asset into the virtual world in some form of representation. That can be purely data, that can be a digital twin, that can be any other form of digital asset. Once we have that, we have to make sense of the data, because if we don't, when we just collect data without really using it in a value-added way, it's not an asset. It's a liability. It costs money to store that data. It overwhelms people, and then it's basically worse than not having the data. So utilizing the data utilization is a key aspect or key principle of smart manufacturing in our understanding. So when we now think, why is AI right now so hot? Well, our perspective there is that there's a few technological advancements that really enable this this growth in AI solutions. And on the one hand side, again, the connectivity, and Metcalfe's law partly supports that. That the more assets we have connected, the bigger our network grows. The number of users increases, the better we can make use of that. On the other side, we have the performance component, and most of us have heard of Moore's law. The increase of processing power. Even so, some now say, hey, we're beyond that. Nevertheless, the key message is, well, our computing or processing performance increases significantly over the last years, and this basically leads to that. We now face manufacturing systems where the cyber-physical production systems connects users, assets, and other items on the shop floor. The data transfer is rather efficient. There are standards developed that allow us to connect. The semantics are well developed, at least to some extent. So we have the data available, and we now can execute these AI models rather efficient in the cloud or on premises, and that's rather computationally efficient. The execution, the training still takes some computing power to be done. Both these or these developments on connectivity and performance, they really built the foundation for the advancement of AI solutions overall, but also especially in the manufacturing space. Now that we said, hey, the technological advancement really benefits the development of AI right now, is AI a new technology? Well, no, it's not. As early as the 1950s, we saw AI solutions and machine learning pop up, right? And certain aspects being developed. I think it was 56 when IBM had their famous paper on a game of checkers, and I mean that's over 50 years ago, right? Or 60, more than 60 years ago. Nevertheless, right now AI is still hyped and on top of the Gartner hype cycle. So what happened? Well, we had certain progress being made, a lot of expectations, and all of a sudden we hit that AI winter. Some say we had two winters. I put them together. And in essence, AI didn't live up to the expectations. And some funding agencies said like, hey, we won't invest in that any longer. And that led to, well, the AI winter where nobody basically worked on this or could work on it with the lack of funding. And not until the mid 80s when multi-layer neural networks were developed, this picked up again, and AI really was back on the research radar. Then new and exciting technologies were developed, including support vector machines. Of course, the very famous deep learning that is right now still on top of the hype cycle as well. And where we are right now, some call the AI spring. Others already refer to, hey, the expectations are so extreme that we might be at the verge of a new AI winter when the expectations don't meet reality. It's always hard to predict the future, right? So we will see where we head from now on. All right. When we now think AI and machine learning, what's the difference? On the left-hand side, you see a PowerPoint. On the right-hand side, you see code in a Python script. And the popular opinion often is like, hey, when it's a PowerPoint, it's artificial intelligence. Hence, this presentation is called AI because it's a PowerPoint. And when it's coded and when it's really like an algorithm, then we're specifying that as machine learning. Take it with a grain of salt. That's obviously not 100% true. And there's exceptions in both ends, but it gives you an indication what the focus areas are. When we look at the more detailed definitions, artificial intelligence is defined as machines that can perform tasks in ways that are intelligent. And these machines, in this case, are not just programmed to do a single repetitive motion. They can do more by adding to different situations, okay? So kind of like self-learning Terminator type of machines. On the other side, machine learning is understood as a branch of AI, but it's more specific than the overall concept. Most machine learning is based on the idea that we can build machines to process data and learn on their own without our constant supervision. So the frame and the system boundaries are more defined here. And in my lab and with some colleagues, we often refer to AI or the general understanding of AI as general AI, aka a Terminator type of self-learning, intelligent, human-like system. And then specific AI that more resembles the machine learning focus, where we have a certain problem, we have a data set that represents that, and we have a certain objective that we want to achieve. And that is more on the machine learning side, where we can get more realistic results. And in manufacturing, as you can imagine, the latter, specific AI, is more prevalent. To visualize that a little bit, when we want to put that into a trivial representation, we could understand the human head as artificial intelligence, right? Machine learning would represent the brain, and the different cogs in the brain that work together could be the different algorithms that are available. Here I just put deep learning as an example. Okay. Semantically, when we look at the relation between key AI terms, we have the foundation for everything, statistics and mathematics, which are the basis for machine learning. And there are different machine learning methods: deep learning, random forest, support vector machines, you name it. Machine learning itself is a subfield of artificial intelligence. And then when we add visualization as a basic technique or technology, we can add data analytics, which we can use machine learning for our data analytics problems. Okay. So when we now think machine learning, we're now at the specific AI portion. How is the process generally structured? Well, it all starts with getting data. We have to acquire a data set, right? We have to collect data because both the algorithm and the model is fueled by it. Then we have to pre-process the data, and that includes feature engineering. Oftentimes we cannot just, push the data into the model and expect good results. Then we have to select an appropriate machine learning model. We have to train the model, then evaluate the model. Like, does it actually do what it's supposed to do? How good is the prediction? Then we can tweak the parameters to get the model to perform better. And then once we're satisfied, we can apply it in our shop floor, in our supply chain applications. This, of course, is not a straightforward process. There's a feedback loop within, and there's different ways of supporting, for example, the model selection. That is, there's ensemble methods or so, where we use machine learning to find the best model. One thing that I want to stress here is that oftentimes when we look at AI or machine learning projects, we see that people focus a lot on the model selection and the model training. I believe, and a lot of my colleagues support that and agree, is that's a mistake. We should prioritize the data pre-processing and the feature selection, especially in engineering application, where we have years or decades or hundreds of years of experience and knowledge available that could help us to put context to our data. And that is something that I always try to stress and get people to listen to. All right. You now see just there's a variety of different tools available. I just distinguished here supervised and unsupervised learning. There's, of course, also reinforcement learning and others. But what I want to show is that a lot of the methods or models, algorithms, can be used both supervised and unsupervised. The difference being, in a supervised learning approach, we have an expert available, a teacher that can label the data set and allow us to train the model in a different way to unsupervised methods. In machine learning, we mostly apply supervised learning because we have the teacher readily available. We have a lot of knowledge that allows us to contextualize the data and therefore train our models better. All right. Now let's take a step back and think about, okay, when we talk manufacturing, when we talk smart manufacturing systems, the granularity matters, right? And when we look at application of AI solutions, at AI support on the part level, we have a lot of understanding of how the part should be, what the quality parameters are, how the processing works, and so on and so forth, right? So we understand a lot of that, and it's mostly a technical issue to apply or develop an AI solution to support that. Similarly, for the machine tool data analytics, we have a good understanding of the majority of processes. Machining and so on are well developed, well researched. Of course, there's still progress being made, no questions asked, but we have a solid understanding of how the physics behind it work. So it's also a more or less technical development where we collect data from the machine, put it in context, develop our model, use the prediction to improve. But the higher we go now in the manufacturing system, the data diversity increases a lot because we have humans in the field, we have different processes, we have logistics processes in between. And all of a sudden, it adds an organizational component to it. It's not a purely technical exercise anymore. On the factory level, even more, because then all of a sudden the business takes over, and other aspects come into play. We have different products, different production lines, different operators, and that can make a difference. We saw that in a project a few years back where we had a tightly controlled heat treatment process with a quenching afterwards, and the data didn't add up. The prediction model was not accurate at all. And afterwards, like after a long investigation, it was found that the student's assistant that took the part out of the oven into the quenching system with a shovel. There were two students that worked that process, and one of them was rather built and well, large person, while the other one was more smaller and not as built. And they applied the shoveling very differently, and that had an impact on the part. However, that data was not collected because it was not sensorized. It was not part of the core process. Still, it had an impact, and we see more and more of that the higher we go in the chain here. On the company level, we have different factories, different branches, different business units. Politics become more prevalent. Data sharing will become more difficult, and you can imagine that's more of an organizational issue than a technical issue all of a sudden. In a supply network where we talk different companies, that levels that to a whole different level. With, okay, what data can we share? How can we share it? Do we have to anonymize it? All these questions that remain open and need to be answered in the future if we want to really apply AI solutions on that scale. And now industry-wide, where we work basically with competitors, that question is almost all organizational, because you will be very careful to share data that might profit your competition or allow your competition to better understand what you're doing, without understanding the repercussions of that. So when we see that, the higher we go in the hierarchy, the more the problem description shifts from a technical problem to more of an organizational problem, and that is something I feel we will have to focus on more and more in the future. All right, so now nevertheless we said, okay, on the technical side we have good algorithms, we have a solid understanding of connectivity, we have the processing power available. So what is the new horizon? Well, we believe data is still a big issue in a manufacturing setting when we talk about AI. We have almost always unbalanced data sets when we think of quality data, and that makes a lot of sense when you think about it. Of course, we try to produce mostly good parts, so labeling them with ideally 50-50 as not good in a supervised learning model is nearly impossible, and the company will most likely not agree to purposely producing bad parts just to have a better training data set for your AI model. There are workarounds, and people are working on it, including us, trying to use simulated data for to introduce a better balance, like basically simulate bad quality parts, bad quality process data, to augment the real collected data set. And of course, there's data algorithms that try to align better with unbalanced data sets and still create a good prediction. Data quality, well, manufacturing is a complex process. We have a lot of noise there. We have sensors that might fail, that might send wrong items. So the pre-processing becomes really important. Models can only analyze what is measured. Think back of the examples with the two different students that have very different strengths applied. It was not measured, so it didn't apply. It didn't factor in the model, and therefore the prediction was off. Another example is in one of the AI projects that I will introduce later. It was found that in the ranking, the second or third most important driving factor that was found by the model was something that the company thought was not even relevant, and they didn't even know why they included that data piece. Nevertheless, the algorithm found that it has a big impact on the quality of the part. And with further investigation, they found, hey, we never expected that, but this part of the process has a big impact on the overall quality outcome. Okay. If that data would not have been included, it could not have been included in the analysis, and we would not know this aspect, right? And then the prediction would always be flawed. And there's a bunch of other manufacturing-specific issues with data that need to be addressed in order to really advance the field. Why is it so exciting that to use AI in a manufacturing setting? I want to stress here this high-level Gartner overview over the hindsight, insight, and foresight perspective, and look at what the new promise is. Like right now, we are fairly good in descriptive analytics and diagnostics. Predictive analytics, especially in the maintenance space, is developing rapidly and shows some good results. But the future really hopes for this prescriptive analytics, where we not only understand when and what will happen, but what can be done to prevent it or to mitigate that. And that is really, especially when we think of black swan events, a really interesting new horizon that will show what AI is really capable of if we succeed to do that. Obviously, has a lot of value for the business, but it's rather difficult to achieve. So that's good news for universities and other research focused folks, because that means there's a lot of work to be done in that space. All right, that was the background and the Quo Vadis AI, and now we will move forward to the examples of AI in smart manufacturing systems that I have prepared. The first one is exactly the one I mentioned before with the feature ranking of state drivers. We looked at a multi-stage discrete manufacturing process and applied support vector machines in a sort of feature ranking to identify the driving parameters of such a multi-stage process. And the output was then a ranking of the most important features as an input for the manufacturing engineers and process planners to optimize the production. In one of the scenarios, we got an anonymized data set. So basically, there was a parameter 1, 2, 3, 4. We didn't know exactly what parameter that was. It was normalized, and we applied it to our system or our model, and provided then a ranking back to the company that gave us access to that anonymized data set. And that was then a ranking of parameter 15, number 1, parameter 12, number 2, parameter 18, number 3, following that impact on the quality outcome. And first, the company said, like, yeah, we know the first driving factor, we know 3, 4. But number 2, we don't believe that's important. We normally don't even include that in any analysis. That made us go back to the drawing board and were a little bit frustrated because we didn't understand why that happened. But a few weeks later, I believe 1 or 2 weeks later, the company called and said, like, hey, we looked further into it, and it has actually an impact, right? We just didn't know it. So the model was accurate and enabled them to better understand their own process in the end. The second project first focus was on connectivity, to basically get remote access to manufacturing assets in the field to upgrade existing units. And then over time, the project evolved, and it now can the data assets. It's a heater dryer system, has 6 temperature probes in it. And that allows us to now stream the data continuously at a high resolution in the cloud, and then for us to analyze it for certain events. And there we did quite some work on automatically detect these events. First of all, to use a moving window approach to identify the different clusters, and then work with the experts to label the clusters. And in the future, we hope to apply an automated neural network approach to label them and to predict them. So again, connectivity is key. Once you have access to the data, you can do a lot of things, and that will help to make that process more more resilient, and more robust. All right, the next slide here is a project that will kick off in December, where we look into a grinding process, and the objective is to save energy on large like end gears, which take like 11 to 17 hours to be manufactured, and 33% of the manufacturing costs can be attributed to energy. Our approach, or what we try to do here, is to merge the physics-based understanding of the grinding process. Grinding is a very old process, and we have a solid understanding of the physics behind it, and merge it with a data-driven model to optimize the prediction, and then to structure the dressing, sharpening, and grinding of that gear. The goal is that we can save 15% of the energy consumption to produce one of these gears. We do that work together with Clemson University and Itamco Manufacturing in Indiana. All right, now what do all these examples have in common? Well, all are based on a rather specific problem, right? So when we look back and remember what we talked about before, these AI applications can be understood as specific AI, as in manufacturing, most applications are, right? We have a defined problem, we have a defined objective, and we apply an algorithm to help us gain insights in that. All right, now moving to the last part of the presentation. I would like to give you a quick outlook on, or my take on what I expect in this space to happen. Some is more short term, some is more long term. You will see, and some is a little hopeful. So I wanted to keep that open to inspire and cause some discussion, ideally. So when we look at learning, we need lots of data, right? And Tesla is a prime example how they utilize their products to collect a massive load of data. VW recently said the reason why Tesla is so ahead is because they continuously stream data from all the cars in the field, and that helps them to fuel the development of their autopilot. Hey, we need an autopilot for manufacturing, right? Our manufacturing machines and assets should stream data continuously, put it in context, and that will help us tremendously to develop better models. I believe, and I will defend that humans are and will remain key in manufacturing, as operators, as maintenance, as teachers, and as planners. The human ingenuity is key, and upskilling of manufacturing experts to get them better understand the applications of data-driven methods is crucial. The manufacturing understanding and the understanding of the process and the physics behind it, the art of manufacturing, I believe has a huge impact, and it's a huge opportunity for AI development. We cannot let the data scientists win. The manufacturing engineers have to take over. That's provocative and joking in some sense, but manufacturing is hard to grasp, and experience is hard to replace. So let's work together and not fight this. All right, we see more and more applications of dedicated AI chips. I think NVIDIA brought some out, Google has some, that allow us more applications, higher adaptability. We see more applications on the edge and fog, so we don't have to utilize the cloud and streaming so much. This will be rather exciting. One little small passion project of mine, but I really hope we see some development soon, is automated design of personalized products. When we apply the product lifecycle model, a lot of the products today collect data, user data, and understand how the user really interacts with them. And that offers a lot of opportunity, I believe, to face that back in the design phase and the manufacturing phase, to automatically adapt the current design and then produce a personalized product that is really based on the unique requirements of the user. Sport shoes, implants, you name it. There's a lot of theoretical applications. Now we just have to make it a reality. Just in quotation marks, obviously. An interesting thing then, when we talk about personalized products, and we see more and more into like customized products, at least, how can we reach a higher level learning? How can we transfer the learning from different models, from large data sets of monolithic products, to can we learn from the production of a boat and transfer that learning of the manufacturing process to the manufacturing of a TV, right? That higher level learning, that transfer learning would be or is extremely interesting to explore. All right. One thing that goes back more in the general AI space is that AI will support us with the data pre-processing and insight development, more of an end-to-end solution. There are, of course, progress being made here, but I believe we're still out a few years or decades from something that we would really trust. That the other very far in the future aspect is that AI develops new AI solutions independently and includes the business understanding and business objective. Scary, but also appealing at the same time. I think that's far in the future. And now, before I wrap up, I saw Robert has a question. I will answer that right at the end. I just want to give 5+1 advices for the successful use of AI in smart manufacturing systems. The first one is learn to walk before you run. Right? Do small projects, learn what works, what doesn't work, how the process works, what you need to know, what skills you need before you hedge all your bets in one basket. The AI applications that you apply must be business value based, so they must address a real problem, because why else would you do that? AI vision models prototypes are comparably easy. When we talk AI solutions on scale, these are tough to do. When we start with specific AI, so machine learning in smart manufacturing systems. Don't engage in the general overall governing AI. That is probably something that is doomed to fail. Don't do everything yourself. Know your strengths. Collaborate. There's great opportunity to collaborate with startups, with academia, especially for larger companies or traditional manufacturers. Startups are great because they oftentimes have a lot of experience in the data-driven setting and the digital space. And they are very interested in getting their foot in the door and getting some use cases to show what they can do. On the other side, it allows you to interact with a group that has that knowledge and is very agile to adapt to the requirements. Academia, of course, from my own interest, we are always interested to ground our research in the real world, so always happy to collaborate. And the last one, and most important one, AI is no silver bullet. When you don't understand what you really want to do or what you try to achieve, that is probably a bad starting point to apply AI. It will not solve everything. It is a tool, and you have to understand where this tool makes sense. Okay, I see you have a bunch of questions. Let me go through the last slide that I have, and then we engage in the questions. So the key messages: be aware, AI is currently at the peak of inflated expectations. That can go either way. We need to differentiate between general AI, aka the Terminator, and specific AI, which is the more realistic machine learning approach that we take in manufacturing normally. Artificial intelligence versus machine learning, what's the difference? That we predominantly use supervised machine learning in manufacturing because we have the experts and the expertise and knowledge available. Data quality and quantity is key. Pre-processing as a step in developing your AI solution is more important than the machine learning algorithm itself. And keep in mind what you want to achieve. Is it a hindsight, insight, or foresight application? All right, that concludes my presentation. Now I would let me see what questions arise here. In what areas of industry do you think AI will make the biggest impact in the near future? That's a good question. I believe a lot of engagement right now is on the one hand side in the supply chain, value chain applications, also due to the COVID pandemic. So we will see a lot of development there because there's a lot of interest and a lot of pressure to find new solutions, to problems. And personally, I think a lot will be done in the operator 4.0, the space where humans interact with AI. So that I think are areas where we will see some more engagement and a lot of impact. Maintenance is always a big topic, and we already see some very good applications and very impactful applications, and that will probably continue to develop. There been much AI use in support functions like supply chain management. That connects to my previous answer. Yes and no. Some areas are supported, but I think, or in my experience, in my limited experience in this space, I'm more on the manufacturing side. I think a big problem is the data exchange, like the willingness to really exchange data across the supply chain or supply network. And that I think is the next big hurdle to say, okay, how can we do that? Is there a broker needed that secures that exchange? That prevents a little bit the application of AI there. But I'm quite certain that we will see a spike in applications here in the near future. Okay, here more comments from YouTube. James Nelson asks, with regard to human capital, will production workers need to have fuller understanding of statistics and quantitative analysis to be able to maintain top performance of production machines processes? Excellent question, Nelson, or James. I don't think they, like, my understanding is that the typical operator would not need to really develop the models and have that deep understanding of statistics and the modeling behind it. But I believe operators in the future have to have a base understanding of where the insights come from, what they're based on, and how they can interpret them to make them actionable. A lot of the AI solutions are still black boxes, and in manufacturing, we don't like that. We want to understand why the computer tells us to do something, right? And in that space, I feel having that explainable AI and having the competency on the shop floor to understand why the AI is telling you to do X, Y, Z, to change the parameters or to optimize your production in a certain way. We need to qualify and upskill our operators in that space. Not make them full-scale developers of new algorithms, but give them the tools to interact with the AI. That would be my take on that. But that's a very difficult question.
And Thor, is that your precious child that was on the screen just behind you?
Yes, that's Dominic. He promotes our book very vividly.
I was going to say you have to order Dr. Wuest's book. Yeah. Thank you so very much for sharing the information that you have with us today. Very enlightening, and I'm so glad to hear that humans will not be replaced anytime soon.
No, I'm 100% certain of that. Thanks so much, Teresa, for having me.
Thank you. And if anyone, we will have all of Dr. Wuest's information up on the website. So if you do want to order his book and you haven't had a chance to write that information down, we'll have it available for you on the IMSI website.
Or when you want to reach out, feel free.
Right. Okay. Thank you very much.
Thank you.
And guests today, thank you so much for joining us for the brief this morning of all of the different topics of information that we've covered. And we look forward to having you join us this afternoon. We're going to be back about 12:30. Give or take, with an action-packed and information-filled afternoon. So take a break, and we will see you around 12:30. Thank you very much.